So, I ran out of time with my camera person yesterday, so I'm going to improvise the rest of this, or try to improvise the rest of this. So I'm going to generalize our invariant interval, our arc length, or interval between events on space-time, distance, to a curved space. It's described, let's get that camera focused better. ds squared equals, you sum over the mu and nu, g sub mu and nu. I'm going to say uv. I write it as mu and nu, but in my head I say u and v. And we sum over that. So now the metric coefficients become functions, demonstrating curvature, which in flat space that will just become c squared as per normal in the plus minus 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 metric signature. Plus, I'm going to only consider, I'm only going to consider a diagonal metric tensor for the demonstrational purposes here. So you sum over the spatial components, g sub I dxi squared equals ds squared. Well, let's divide out by dt squared. dt squared over dt squared. So a path is defined by position vector as a function of time, and this path takes you from the position vector at an initial point, this is the function of time, the graph so to speak, just a 1D example, to the position vector at the final time. And so, kind of like with the arc length, the way that these positions vary with time defines the path, which enables us to take the square root of that, gx plus I g I. I'm going to write xi dot squared times dt, and the path uniquely determines this. Integrate from f to ti, and that will be our interval there. So this is a functional, and it depends upon what our path is. The actual value of it depends on what our path is. So, but you notice that since these metric components just depend upon our positions and our velocities, that we can basically we can write this more or less as a functional of the positions and the velocities here, assuming that there's no time dependence on here, the spatial positions. Well, I'm going to define the action functional. A equals b times s, which is our interval. B is some constant. B times ds. And when you vary A, does nothing to the constant because it's a constant. and this is our interval. As we said, the path that's chosen minimizes this functional, this arc length, this invariant interval. Minimizes it, which means that, when you vary the path slightly, keep the endpoints, but if you vary the path slightly, new path, it won't change this. It's kind of a generalization of the idea that the extreme points, the extreme points of a function are where the derivative of the function goes to 0. It's going to be 0 because our path is defined as the one which makes this go to 0. So our action, consequently, just basically just a constant times ds, is going to also be minimized. Well, I'm going to define now our action. We're going to rewrite our action as tf integrated over the time of the path, ds over dt times dt. Our constant times ds over dt, as we said, is just b g o x plus g I x xi squared summed over I. Well, this is just a function of the positions and their corresponding velocities. And we call b ds over dt the Lagrangian here for our purposes. Now, there's more generalizations in field theory and all that stuff, but for our purposes, for this demonstration here, this will suffice. So we're going to write our action as tf ti l xi x I. Some of the coordinates and then their velocities. Well, the idea is that when you take this path, which is defined by the form of x sub I as a function of t, and x dot sub I as a function of t, when you vary that path slightly, it's not going to change. It's not going to change this. So we're going to write xi plus e it's going to take the time derivative of that right there. So minus L xi xi in the limit that becomes infinitesimally small. We can consider up to first order, at least up with the xi part, as x sub I plus e I epsilon plus the first order correction e sub I derivative, partial derivative of L with x sub I. And then that too will be similar. You'll take the partial with respect to the velocity. Plus, and then the change in the velocity, a total differential. And that's just our regular Lagrangian. And you're left with equals and it should equal 0. Well, I'm going to rewrite the epsilon as delta x. I just, well, that's not necessary. Okay. What we're going to do here is differentiate by parts. No, we're not. Okay. Don't listen to me.